last two videos, maybe even one if I can do this in one. We're going to look at the combined gas law. And one thing I want to show you here is this simulation, states of matter. So if I flip to my website, states of matter basics. So what you can see here is I can change the volume at the top here, moving this up and down. I can, and that then we can measure the pressure. I can also change the temperature, and I can have it in degrees Celsius or at Kelvin. I can also increase the pressure by adding more particles. Now and I can heat and cool down the bottom. Now this is a solid. So we want to study gases, so we need to make this into a gas. This is neon. You can actually have a look at some of the others. But what I want us to notice here, so increase in temperature, look at them all moving faster. Okay, we're at 50 Kelvin. It's a gas, minus 223 degrees Celsius. And you can see the pressure here is around 2018 atmosphere. I'm not heating it anymore, so it's just going to stay at the same temperature. But what we can do is we can show some of those effects. So if we've got constant temperature now, no, this is what I want to show you. Watch the temperature as I increase the pressure, decrease the volume, increase the pressure. But you're noticing the temperature is going up as well. Okay, same if I decrease the pressure, increase the volume, decrease the pressure, temperature goes down. Okay, so what I'm trying to show you here is Boyle's law, Gay-Lussac's law, and Boyle's law, Charles's law. They all are interrelated. You can't just look at pressure and temperature. They all kind of work together. So when you change one, you change all of them. So let's go back to that document I have. And the key idea here is if you change pressure or temperature or volume, the other two values also change. So to make the calculations easier, they joined Boyle's, Charles, and Gay-Lussac's law together. So it doesn't matter if the pressure changes as well as the temperature, you can still find the volume of the gas. So quickly, there's our three laws, Boyle's law, Charles's, and Gay-Lussac's law. And what we're looking at is the combined gas law. Okay, by putting these together, we know that, and so with this side here, V divided by T is K. So we basically just keep making K the thing. Same here, P divided by T is K. So basically, and we know P times V is K. So with all those things, if we put them all together, we end up with the combined gas law that PV over T is equal to K. And then we go to that changes one. We know that it's going to be constant for the same amount of particles. So it's really important you don't change how much you've got in there, because that will change them again. So P1 V1 over T1 is P2 V2 over T2, okay, because the constants need to be the same. So here's an example of us using this equation. So the student measured the pressure and volume of carbon dioxide at 25 degrees Celsius, T1, 25 degrees C, and that is 298 Kelvin, which is what we must use. 96 kilopascals, P1, 96, kPa, and 500 mils. So 500 mils equals, it's hard to write there, equals 0.5 litres, okay? So I'm going to write that there, 5 litres, has to be in litres, okay? The gas was then heated to 450 degrees Celsius. So here's 450 degrees C. We need it in Kelvin, so we need to add 73. And if we add 273, oops, plus 273 is 723. 23 Kelvin. Okay. Okay, what else we got? The volume increased to, how did it increase to that? I don't know what I've done. Pressure and volume. Maybe it was meant to be decreased. I don't know. That's what it's, we're just going to use the numbers as they are. But 338 mils is not an increase in volume, it's a decrease. Anyway, okay, so that will be 0.338 litres. Okay, so we're looking for P2. Rearranging our equation, we want P2 on its own, so we divide this side by V2 and times it by T2. And when we do that, on this side we cancel out, and on this side we get it. And so we end up with our equation V1 times P1 times T2, then divide that by T2 divided by V2, times V2. So let's put all our numbers in now. So oops, I must have had my hand too close, sorry guys. 0.5. Oh, I love it when it doesn't want to work. 0.5. Weird. Just be weird for me, don't you? Okay, let's go. 0.5 times, what was it? P1 was 96 times 96 times, oh my gosh. All right, I give up. Suddenly it doesn't want to work. So 0.5 times 96 times T2, which was 723. Okay, so that thing, and then we do that divided by, oh, come on, the eraser doesn't want to work. All right, divided by T1 times V2. So T1 was 298 and V2 is 0.338. Oops. What have I done? I've typed something wrong here. Times. Okay. So let's put all that into a calculator and we'll see our result. 5 times 96 times 723 equals 3,470. I'm just going to write that down. 34,000. Oh my gosh. $704 divided by, that's 298. Oh wait, can I change this to like scientific? Dude, did not realize I had that option. Let's do that again then. 0.5, wait, parentheses. 0.5 times 96 times 723, close parentheses, divided by, open parentheses. Oops, oh, I know what I did wrong. I see it now. Oops, okay, let's start again. Where's clear? There, sorry. All right, 0.5 times 96 times, oh, anyway, I've done it again. Parenthesis, 0.5 times 96 times 723, close parentheses, divided by, open parentheses, 298 times 338. No, that's not right. I just realized. Backspace, backspace, backspace. 0.338. Close parentheses. There we go. So our answer is 100 724. Let's just copy that. Okay. Sorry, I realized my mistake here. That was 0.338. Ooh, guys, these are things to keep a check on. All right. And so that is us just using that equation. Okay. Now, the next bit that has to do with this is we're going to be looking at how all this fits together when we even consider the fact of moles. So one rule to rule all of them. Rule them all, like I think of my Lord of the Rings thing. So the idea